All right, 614, 615. This is Gibbs free energy part 2. I think I needed to add one more little bit onto what we did last time. It's been a long, kind of crazy day here. All right, so what I want to do is, let's see. Let me just get all this stuff going. All right. Oh yeah, we're looking at the summary paper that I gave you, and I was telling you I need to go over a few more of those in the summary paper first of all, and then I'm going to mention one thing back to the notes quickly, but it'll be pretty simple. Okay, so there's a question, H2O. Oh, there was a question I did not do. You know what? There's one question I did not do for the H2O problem, and it said this. Okay. It says on, back to example A, prove mathematically whether or not ice will melt in these conditions. And again, 1, 2, 3, 4, 5. I forgot to do a 6. I noticed that right here. And 6 just says, it says, at what temperature does equilibrium exist for this reaction, H2O solid changing into H2O liquid? Well, I have not mentioned anything about equilibrium until this next page. But the delta H was, what was it, 6.04. Delta S was 22.1. Not mixing that up this time. Joule mole Kelvin and kilojoule per mole. Okay, well, actually, I kind of did tell you when I did the other problems, I kind of did tell you this a little bit. But at equilibrium, delta G is 0. So if delta G is equal to 0, then that means that the reaction will occur spontaneously. It actually means you're at equilibrium. So it will melt, but it will also do the forward and backward will both occur. You have both things present. So anyway, if you want to find the temperature at which equilibrium exists, here's what you do. Now, a lot of this applies to the equilibrium chapter we'll do later in the year, but right now you can do this pretty simply. You let delta G equals 0. So if that's set to 0, then delta H is 6.04 kilojoule per mole minus, and you're trying to find the temperature, and then times delta S, and delta S is 22.1. Now remember, you got to divide by 1,000 in order to put it in kilojoules, because it's in joule per mole Kelvin. So if I want to get kilojoule mole Kelvin, I'll have to divide by 1,000. All right, now let's solve for that and see what happens. So 6.04 minus 0.0221 T. Okay? Now, of course, negative 6.04 will go over here. Algebra. Negative 0.0221 T there. Divide both by 0.0221. 0.0221. Okay, or negative technically. It'll be a positive number. 6.04 divided by 0.0221 negative is 273 equals the temp. What do you know about that temperature of 273? That's Kelvin. Ah, that's 0 Celsius, isn't it? Aha. So, ice and water will be in equilibrium at 0 degrees Celsius. That's the temperature at which equilibrium will exist. Now, sometimes they ask you also, which process, the forward or the backward, will be favored at that temperature, above that temperature, or below that temperature? They like to ask that a lot. So I like to make a chart when I do a problem like this. This is the easiest problem, to find the temperature. That's easy. But then otherwise, you can make a little chart, and I'll show you how to do that. So at temperature equals 273, will I fit it on here? Delta G equals 0. Delta G, that's all you have to say. Delta G equals 0. So system at equilibrium. The system is at equilibrium. Both the forward and the backward reactions occur. All right. If you're at a temperature, can you read that? At temperature, this is getting so small, this chalk. I'll try to keep it though. At temperature greater than 273, what happens to delta G? Okay, let's think about that for a minute. What happens at a temperature greater than 273? Well, if I come over here, one way I like to think about it is, let me put a number in for the temperature. Like we know the temperature is 273. So just kind of think mathematically here a little bit. We know that 273 times this and that equals 0. We just solve for that. So at 273, delta G is 0. If you have a bigger number here, is delta G going to be positive or negative? If I put in a real big number like 200, how about 273,000, like a really, really high number? Well, now, think about like I showed you before, your negative term becomes really, really big, much bigger than that. So they're not going to be equal and opposite. They're not going to be 0 anymore. Now it's going to be negative. At temperature greater than 273, delta G is negative. You can say delta G is less than 0 or delta G is negative. Okay? So the opposite will also be true. If I put a really small number in there, when I put 273, they're equal. If I put a really small number right here, like 2 or something, well then now delta G will be positive. So at temperature less than, at T less than 273, delta G is going to be positive. Or you can say delta G is greater than 0, delta G is positive. Now, this is a mess. I'm writing all this on the board right here. But I'll just kind of, let me get all this other part kind of out of there for a minute to kind of restate it. So here's a little chart that you want to be thinking about. If you're at exactly 273, delta G is 0, the system's in equilibrium, nothing's favored. If you're at a temperature greater than 273, delta G will be negative, because if that number is really big, like 373 or whatever, you can just try it, you'll get a bigger number. It's negative. The negative term's better. It's negative. Negative means it's spontaneous in the forward direction. So, spontaneous forward. All right. Another way to say it is the products are favored. The product side of the equation are favored. So, forward reaction is spontaneous. The products are favored. And then the opposite is true. If it's positive, then that means it's not spontaneous in the forward, but it will be, if it's in equilibrium, it will be spontaneous in the reverse. Okay, so if delta G is positive, spontaneous backward. And the reactants will be favored. And what that means is you're going to produce all solid. That you're not going to have any more of that. Reactant is favored. Favored or produced. You can put that as well. Okay. When I knew I need to add a little bit more, that's why I came back here to do this, and I just realized, wow, I didn't show you that chart. So, in reality, on an AP question, they have part for Thermo A, B, C, D, E, sometimes A, B, C, D, E, F. They will ask you, usually on the last one, they might ask you one of these. Find the temperature or find what's favored below the temperature, what's above. They're not going to ask you all of them. So if you can make the chart to figure out what all of them are, you'll blow away anything they can, any question, you'll have everything blown away that they can ask. You'll have it all done. All right. Now, on the next page, there's another type of problem, example B. And I was about to end earlier, but then I realized, oh, I better do that. Okay, example B. And it says bromine liquid going to bromine gas. Now, again, there's the equilibrium there, yeah. And it says delta H is 31 kilojoule per mole. If it seems repetitive, I won't do the whole thing, but I'll just check if there's a reason. And then delta S is 93 joule per mole Kelvin. 93.0 joule mole Kelvin. Hopefully I copied it down right there. All right, the first question, I have to look at my computer. That's why I keep looking down here. It says, what process is favored? Oh, okay. At that temperature, above that temperature, and below that temperature. You know what? I think that I will not do this part. It's just like what I just showed you a moment ago. What will be favored at that temperature, below that temperature. I'll give you the answer key. You'll be able to read on it and see. But I'll just tell you, the key to it is you're going to use this equation again. and you're gonna solve for the temperature. And the temperature you get, you put in H, you're going to put in delta S, and then of course you divide that by 1,000, and put delta G as 0. That will tell you the temperature at which equilibrium exists. Then you got to think about what will do the T value, make it will it make it delta G positive or negative if it raises or lowers. So there's no need for that one. All right, number 4 is a good one for you to do. And then number 5, and that's pretty much the whole thing. You can go back through, yeah. So the back of the, example B, I mean, there's no need for me to do that. In fact, I'm probably going to release the answer key really before it's due. It'll probably be on there. You can look at the answer key and just, if you want to skip example B, that's okay. I'll tell you that. But you're going to get the answer to it anyway later. So, but for sure, do the next one. Do number 4 and number 5 on the worksheet. Number 5 might have been eliminated, but I don't know. But on the back of the summary page. So work those problems as well, and you're in great shape to cover every single thing. All right, there's one last thing to tell you, and this will only take about, I'm going to guess it's only going to take me 1 minute to tell you this, okay? So you'll be happy. This will be a short video. All right, in your notes, back to the notes again. I told you we'll do 6:14 and 6:15. Well, look at 6:15. Okay. All right. I don't have to even do anything because this is so easy. All right, I'll show you. 6:15, they're wanting you to calculate, well, look at letter A. The following reaction is carried out at 25. Calculate delta H, delta S, and delta G using the following data. All right, this would take some work to do it all. But what you have to do is, first of all, you got to find delta H, all right, by using the equation, this one. Delta H equals the sum of N times the H of formation minus the sum of N times the H of formation of the products minus reactants. Same thing we did before. So, I mean, you don't have to actually go through and do all this, but you could use all those 3 values and find delta H. Then use all these values and find delta S. Same way, with the same equation, but with the S, S, and S. Okay, you subtract all that. I mean, it's a lot of work. But then what you do to find delta G, you just take delta G as delta H minus T delta S. You plug in your H and your S to find it. I'm not going to be asking you that, because if I do, that would take you forever to do that. And so I'm not even going to, maybe on the extra credit you might see one pop up. Second method to find delta G is if I just give them, oh no, let's see. Oh, no, here it is. Guess what this is? This is a Hess's law. You can do Hess's law, and instead of delta H values, they give you delta G values. And guess what? It works exactly the same. So there's no need, but if you don't be surprised if you see a Hess's law with delta H, so you can do it. Delta G, you can do it. Delta S, you can do it. And then the third method is by finding it by the delta G of formations. Every element has a free energy of formation, a standard free energy of formation, and it's the same as this one. Products minus reactants, nothing new. Same thing you did with delta H, with delta S, and there'll be one on the worksheet for you to do today for delta G. It's interesting to note every element in its standard state has a delta H value equal to 0. Well, they also have a delta G value equal to 0 if they're in their standard state. Uh-oh, I said 1 more minute, and I think that was 2.5 or 3. But anyway, that's all. That is all, you guys. So I hope this summary and this kind of wrap up helps you as well. So I hope you do well on Thermo. I'll see you guys.